Hi, my name is Salma Genis, and I will be doing a presentation on the conservation in mechanical energy for my Physics 128 course. Mechanical energy is the energy that a system stores because of its reliance on position. In order for a system to have mechanical energy, it can only rely on gravitational forces, can't have anything pulling or pushing on it, cannot be interrupted by friction or air resistance, or at least it has to be of negligible value. Mechanical energy relies on kinetic energy, which is the energy for motion that an object has, relying on the mass of the object and the velocity. The potential energy within mechanical system is the possibility of energy because of the position that the object is in. So we're going to use some formulas to talk about mechanical energy because non-conservative forces do not act on the objects in this system. Work of non-conservative forces is equal to 0. And then that means our total mechanical energy is going to come from our kinetic energy, movement, and then our potential energy, which is position. In this system, energy is conserved. So energy at the beginning will be the same as the energy at the end. That means the kinetic energy and the potential energy at the beginning of a system will be the same as the kinetic energy and the potential energy at the end of the system. But that does not mean that they are equal to each other. Like kinetic energy 1 is not equal to kinetic energy 2. In that sense. To further understand this topic, I will be showing a demonstration. This is just the introduction of what I will be doing. And let's see if I can start the video.
Hi, my name is Salma Genis, and this is my demonstration for the conservation of mechanical energy within a system. In this system, there is a negligible amount of friction on the material used to make them. It's just cardboard, and then there is no external force when they're just dropping them onto the ramp. What I'm going to be using to demonstrate the different variables within this, within mechanical energy, are these two identical marbles that are expected to have the identical weight, and here are the marbles. Now I'm going to explain both of my ramps. We have ramp A and ramp B. They're both made of the same cardboard material, and then we can see at the bottom here I have laid a strip so that we both know that they're traveling the same distance of 37.6 centimeters, and then the same goes for the height of 31.5 centimeters. They're starting at the same position. And then when we look to the side, we can see that they're not actually the same though, because this one has a steeper incline than this other one B. And because of that, we'll be able to see which marble would get to the base of their slopes first, and then through an equation explain what their velocity would be at the end of their travel.
So with this demonstration, we're just going to talk about the variables and how they interact with each other in the system. So to further explain the scenario, we know that our ramps will have the same height. That means our marbles are starting at the same height. The marbles have the same mass, and they're identical marbles. The marbles will start at the same time. And what we can know from this information, from understanding mechanical energy, is that which marble will get to the bottom first, and which marble is going to reach the bottom with the fastest speed. One more formula that we can benefit from understanding is what kinetic energy and potential energy actually are within mechanical energy. So kinetic energy is half of mass, so the object, and the velocity squared, plus potential energy, which is mass times gravity and height. To answer the question about which marble will be fastest at their end of their travel, we can look at the potential energy and kinetic energy at the beginning of the ramp and at the end of the ramp. At the beginning of the ramp, all we have is potential energy. We haven't moved forward, and therefore the height is what's going to give us possible movement. And then at the bottom of the energy, we've lost our height, so we no longer have potential energy. All we have is kinetic energy because of the velocity that we've gained. Because of this conservation topic in mechanical energy, that means that potential energy from the beginning is going to be the same as kinetic energy at the end. And from our previous slide, this means that mass times gravity times height is going to be equal to half of mass times velocity times the second power, So mass therefore cancels out. Gravity and height are what determines velocity, and since they both have the same starting height and gravity is a constant, both marbles have the same velocity at the end of the hills. The concept of velocity will help us find which marble gets to the end first, even though they're both going at the same velocity. Potential energy is higher at the beginning because of the height, and kinetic energy is higher at the end because of the velocity. We know that from our previous example. If a marble loses height earlier by going through steeper dips, they will gain their kinetic energy sooner though. Both marbles will reach the same velocity at the end. However, the marble with the steeper drop will be forced to reach their higher velocity sooner, which will allow it to reach the end of the slide sooner. The marble 1 on ramp A will reach the end of the hill first. In this video, I'm going to show you the demonstration so that you can see that ramp A will deliver the marble first, then ramp B. This is the steeper one. This is where the drop comes first, and then this one is just diagonally straight. So let's see if I can play this.
My little brother, on the count of 3, drop these 2 marbles down their respective ramps, and we'll, with slow motion, see which ramp travels their marble faster. Record from the side so that we can see how they travel from here.
In each of these scenarios, you could see that ramp A delivered their marble sooner than ramp B, even though at the end they will be gaining the same velocity. I showed multiple angles just in case that human error would be accountable for. Like in each of these situations, you saw that the marble in A reached the end of the ramp first. I believe mechanical energy to be an important concept to understand because of how present it is in our daily lives, in the simple things that we do, and understanding the value of those variables to the result of your system is important, especially to me, where I feel like you could take advantage of that in a physical therapy setting, which I hope to go into. Thank you for joining me in explaining this topic and exploring it through my demonstration. And thank you for the semester, Charlie. And in the end, I will cite my references, which is just my textbook, and I specifically used chapter 6. Thank you.